One of the most challenging aspects of any theoretical course in mathematics is understanding how all of the different ideas relate one to another. In this video, we're going to try and walk a long conceptual road of ideas that gives us a lay of the land of the entire theory of the first half of linear algebra, beginning from questions we can ask about the existence and uniqueness of solutions to linear systems of equations, and ending all the way at the big culmination of the first half of the course, the invertible matrix theorem. So what's it all about? We're going to begin by looking at this diagram, and this is going to be what we look at for the whole video. On the left-hand side of this diagram are going to be the kinds of questions that we can ask and answer that relate to the existence of solutions to a linear equation. In other words, does this linear equation have a solution? Is it consistent? On the right side of this diagram are going to be questions we can ask and answer that relate to the uniqueness of solutions. If this equation does have a solution, could there be more than one, or must that solution be unique? And we're going to see along the way what this has to do with questions about sets of vectors and their span, and whether those vectors are linearly independent, as well as, most importantly, questions about a matrix and what we can tell about the properties of that matrix based on these same questions of existence and uniqueness. So let's get underway. So first things first. We just finished talking a lot about the properties of sets of vectors. So suppose that I have a set of vectors, k of them, v1 up through vk, and that those vectors each live in n-dimensional Euclidean space, Rn. The two kinds of questions that at this point we know how to ask and answer are questions about the span of that set of vectors, and questions about the linear independence of that set of vectors. So that's where we're going to begin this pretty long story. We found out that questions about a set of vectors are typically answered by placing those vectors into the columns of a matrix, and then studying the properties of that matrix. So we've seen how a matrix can be a tool for studying the properties that sets of vectors can have. On one side was the question about span. So the question there was, if you give me a vector b, how do I tell whether that vector is an element of the span of the set of vectors v1 up through vk that we started with? The intuition being that b belongs to the span exactly if we can make b from some linear combination of my vectors v1 up through vk. Right? That b is something that I can build out of the v's, exactly when b belongs to the span. And the formal definition was that b belongs to the span exactly if there exist these weights, c1 up through ck, real numbers, such that those weights determine a linear combination of the v's that adds up to the vector b. So belonging to the span means being a linear combination of those v's. So what does that mean conceptually? So because matrix times vector, you'll remember, means exactly taking a linear combination of the columns of that matrix whose weights are given by the entries of the vector, b belonging to the span of the columns of A means that b is equal to A times some vector x for some x vector, and this x vector contains the weights of the linear combination of the columns that makes b, where all those weights belong to the real numbers. So this leads to the definition that we're going to work more with in the next part of the course, that the set of everything that we can make out of the columns of a matrix, the span, in other words, of the columns of the matrix, is called, on the one hand, the column space of that matrix. It also occasionally goes by the name range, because, as we're going to reiterate in this video, every matrix determines, by multiplication, a function. And to input that function, we take a vector and we multiply it by that matrix A, and A times x gives me the output. And so just as any time we study functions, the range of a matrix is thought of as the range of the function that that matrix defines by left multiplication. What that means is it's the set of every possible output, b is equal to A times x. So it's a set of every b vector that I can make by multiplying A by some x vector. We call that set the range of the matrix, or sometimes the column space of the matrix, because it's the span of the columns. So again, what we just said is that b belongs to the span of v1 up through vk exactly when B belongs to the column space of the matrix that has those vectors as its columns. But that's kind of a circular definition. The more interesting thing here is that it means that B is equal to A times some vector x. And that means that it's in the range of this matrix as well. Now, how do we know whether a vector is in the range of a matrix? How do we know that there exists a linear combination of the columns of that matrix that gives me B? Well, that happens exactly when this equation can be solved. Exactly when that equation is consistent. And so, how do we know when B is a linear combination of some given set of vectors? We know by putting that set of vectors into the columns of a matrix and then asking whether that linear equation that it defines is consistent. And that's really a question, again, about existence of solutions. Does a solution to AX equals B exist? If the answer is yes, then B is a linear combination of the columns of A, and therefore B belongs to the span of that set of vectors, which are the columns of A. So that's step one. That's how we get from asking a question about the span of a set of vectors into answering a question about the consistency, the existence of solutions, of the associated linear equation, where the matrix that plays that role is the matrix that has those vectors in its columns. So if that's the story for existence, what does the story look like for uniqueness? That's on the other side. Uniqueness questions are questions about linear independence. So the other question we're asking right now about sets of vectors is this set of vectors linearly independent? The intuition for linear independence is that linear independence means that none of the vectors in that collection can be built from the others via a linear combination. In other words, we can't explain the presence of any one of these vectors in my collection by being there because the other ones determine it, right? Each one of those vectors is telling its own unique story in this collection. We can't build any of them out of the others. The definition there being that my set of vectors is linearly independent if the only solution to this homogeneous equation, in other words, the only way to make a linear combination of those vectors equal to the zero vector, is to select the trivial solution that makes all of my weights 0. So linear independence means the only way we can build the zero vector out of v1 up through vk is to multiply all those vectors by 0 and add them together. Remember, that always works to make a linear combination of any set of vectors equal to 0, but in the case that that set of vectors is linearly independent, this is the only way to make a linear combination of them equal to 0. And so this really is a question not about whether a solution exists to this particular equation, but how many solutions are there? And the linearly independent case, there is only one solution to this linear equation, namely the solution that makes all of the weights equal to 0. So what does that have to do with the matrix that has these vectors as its columns? Well, the first bit of terminology that we'll add on to that is that linear independence has to do with this equation. And this equation we can see as a matrix vector equation with these vectors as the columns of the matrix. And the right-hand side of that equation is the 0 vector. And because the right-hand side is the 0 vector, we call this equation the homogeneous equation, but we also associate to it a particular property of this matrix. Namely, we associate it with what's called the null space of the matrix A, or sometimes the kernel of the matrix A. By definition, the null space of a matrix is the set of every vector that that matrix transforms to 0. It's the set of all x's such that A times x gives me the 0 vector. In other words, the null space of a matrix is exactly the set of all solutions of its homogeneous equation. So it's what we get when we solve AX equals 0. That's by definition the null space of a matrix A. So what does this null space have to do with linear independence? Backing up a step, we decided that linear independence means that the only way to solve the homogeneous equation for those vectors is to select all of the weights to be equal to 0. And what that means when those vectors are the columns of a matrix is that the only way to multiply that matrix by a vector of weights and get the 0 vector as the result is if all of those weights were 0. In other words, if that vector x were the 0 vector. So, my vectors are linearly independent exactly when the only way to multiply that matrix, whose columns are those vectors, by something, and get the zero vector, is that I've multiplied by the zero vector itself. So my set of vectors is linearly independent if the matrix, having those vectors as its columns, has only the zero vector in its null space. Because in that case, the only way to multiply that matrix by a vector and get 0 is to have chosen the zero vector as the thing that I'm multiplying by. If there exists any other vector in the universe, which when I multiply this matrix by that vector and I get 0, then in that case, a non-trivial solution to the homogeneous equation exists, and by definition, my vectors are not linearly independent. So the null space of a matrix evidently can answer questions about the uniqueness of solutions to its associated linear equations, and therefore the linear independence or not of the columns of that matrix. Now, what's a tool that we can use to determine whether or not a given linear system of equations has unique solutions? Remember, the uniqueness of solutions in a linear system is governed by whether or not that system has free variables. If my system has a free variable, then I can choose a different value for my free variable and get a different solution to any consistent equation that that matrix defines. So if I want my solutions to be unique, in other words, if I want the only solution of the homogeneous equation to be the zero vector, if I want my columns to be a linearly independent set, that must mean that I don't have any free variables. And in order to not have any free variables, what I need to have a pivot in every column of my matrix. So that gives us the basics of how questions about existence and uniqueness of solutions to an associated linear equation are exactly how we answer questions about the span of a set of vectors and the linear independence of a set of vectors. To answer questions about the span, what we really need to do is answer questions about the range or the column space of the matrix that has those vectors as its columns, because it's that set that tells me about the consistency, the existence of solutions of the associated linear equation. Likewise, to answer questions about the linear independence of my set of vectors, I really need to answer questions about the uniqueness of solutions to the associated linear equation for the matrix that has those vectors as its columns. To do that, what I'm really interested in is the kernel or the null space. It's the set of solutions of the homogeneous equation for that matrix. And that set of vectors is linearly independent. Exactly when the homogeneous equation has a unique solution, namely the trivial solution where everything is 0. And that's only going to happen if my matrix doesn't have any free variables. In other words, if there's a pivot in every column. So far, so good. But where we want to push this in the next video is to take the question about unique existence of solutions, in other words, is a certain vector in the span of my vectors, and broaden that out one more step to ask the question, do my vectors span the entirety of the space in which they live? In other words, not is my linear equation consistent for some choice of b that you give me, but might my linear equation be consistent for all possible choices of b? And that's going to unlock the key to the rest of the theory that we're going to explore.